Obviously, do this example. There was one second that I don't. It's okay. I think we're finally ready to go here. How can I help?
Cool. Don't get me started.
So my question has to do with relativity and defining which one is T naught, which is T prime.
Don't even worry about that. I don't. Just recognize that relativity factor is always less than one. And so you just want to know, do I want to make what I got bigger or smaller? Do I want to make it bigger? Divide by the factor. Do I want to make it smaller? Multiply by the factor. For example, if you're dealing with time dilation, remember the example that happened in 1962, where the researchers were expecting all the muons to be dead before they got to campus, because their half-life was, short, and it was supposed to take them, 4 half-lives to get from the top of Mount Washington to campus. But they lived. We didn't have 1/16, we had about half of them. And that's because because they were moving, their clock was running slow. And so it's always going to seem like a longer amount of time in the lab frame. But the moving muon, it's going to seem like, oh, life hasn't passed much. Their clock runs slow, meaning their internal clock also runs slow, and they live longer. Likewise, you can think of that example with Allison Betty. She gets on the rocket and goes to Alpha Centauri at 4/5 the speed of light. Her clock runs slow, and so instead of taking 5 years, we multiply by the relativity factor of 0.6, and it seemed like 3 years to her. Now with length contraction, you know that it's always the longest length in the frame of reference where I can take my sweet time measuring the distance. So if we're talking about a spaceship that's racing up through the galaxy, the longest length is always going to be the length measured by a crew member on that ship. Whereas if you're on Earth or some other planet watching this thing zip past, it's going to be shorter. Meter stick that's going past you really fast is going to seem shorter. And so you want to multiply by the factor if you want to find out what it's going to seem like to someone on Earth that has to measure it quickly, as it goes past. This is how long it is. You multiply by the factor. But if I've measured it, and I measured it to be this long, and I want to know how long would it be for a crew member, well, then you want it to be bigger, because that's where it's the biggest. So then I would divide by the factor to make it bigger. Okay, and the only time that you need to really worry about the prime or the zero or anything like that is in this formula, where you've got L prime B over C squared. That's the time delay between the clocks at the front of the train and the back of the train as seen in the rest frame. Okay, and so if you think of that example with the shootout on the Einstein Express, this is the delay between this is what you would see if you were looking at the clocks as they went speeding past, and trailing clocks lead. And so if the clock at the front of the train is reading 0 or high noon, this is the amount by which the trailing clock at the back of the train is going to already be ahead of noon, afternoon. Does that answer your question?
I think so, yeah.
Okay. Yes, sir.
I've been this one where you use a diverging lens, converging lens, and a mirror altogether.
Whoa. You think that I would do that to you on the exam?
I can see something scary like that.
Yeah, yeah. I can tell you that I didn't do that. Because I felt that there would be fallout from that there would be feelings of betrayal on your part if I did that. So I did not.
Well, if I can do that, I could probably do one.
You probably could, okay. So let's see what we got here. You tell me what you want that problem to be like.
Okay, let's do converging lens first. Then a diverging lens. And then they're
What kind? Converging or diverging?
diverging.
Okay, now I'm gonna need some powers. Or focal lengths, whichever you want to do.
Focal length, let's do a negative focal length on the first one, and positive on the.
Wait,
Positive focal length on the converging lens.
okay. And what do you want that to be?
Negative.
What's that?
Negative 18.
It's gotta be a positive number, it's a positive. That,
Positive 18.
okay. I'm gonna write it as 0.8 meters. Okay, and the negative lens is gonna be a negative.
6.
Okay. And the focal length here has to also be negative because it's a diverging.
14.
Oh man, you're making this hard. Okay, folks, do not blame me if the math turns out ugly here. That is all this gentleman here. So I need some distances.
Go 10 and 20.
10, 20.
Yeah, 110 and 120.
Okay, let's make this the 20 centimeters and this the 10 centimeters. And where do you want to put your object to the left of that first lens?
5 centimeters.
5 centimeters it is, people. 5 centimeters it is. Okay, we're feeling lucky. Okay. So, the first thing I'm going to do is see if people can actually see this on the recording. Let's see. There, that might be better. Okay, so first things first. If we look at light that leaves here and goes out to this lens, the curvature when it gets, let's call this K initial 1. Okay, just keep all these K's straight. That looks like it's part of a circle that has radius of 5 centimeters. And so I would put in 0.05 and 1 over, and that's going to be equal to 20 diopters, positive or negative? Negative, it's spreading out, okay? And then the power of that first lens is going to be a positive 1 over 0.18 meters. And so again, that 1 over is my best friend. And that's going to be equal to a positive 5.55. Now, this is a diverging lens, but it has a focal length of 18 centimeters, and I didn't choose it, he did. He chose to put it 5 centimeters. So that's inside of the focal length, okay? And we know that this kind of lens is kind of messy. Outside of the focal length, you get real images. Inside the focal length, you get virtual images. And so this is going to be a virtual image. So we can see that by doing the K initial 1 plus power 1 is equal to K final 1. And so I've got negative 20 plus 5.55. And that's going to be, oh man, I used to be able to do this. But that's
because that makes sense.
negative 14 point something, right?
4 or 5.
So 20. Okay. So the fact that it's negative means that I'm going to have something that's still spreading out. Okay. Now, we chose ugly. This is spreading out, and this is going to spread it out more, and then this is going to spread it out even more. By the time we get through all of this, it's just going to be whoa. Okay, so if I do 1 over this, I get 6.9 centimeters. And so that means that this image is going to be back here.
Oh, that's crazy.
6.9 centimeters. Everyone okay with that? Okay, now the next thing we do is we say, what's going to be the K initial when it gets to the second lens? Well, I have to use this distance here plus this distance here. Okay, because when that wavefront gets there, it's spread out as if it came from this this virtual image 6.9 centimeters to the left of the first lens. And so that means I'm going to have negative 1 over, I got to take the 20 centimeters plus the 6.9, and that's going to be 0.269 meters. And so if I do 0.269 meters and I do 1 over, that's going to be a negative 3.72 diopters. The power is going to be a negative 1 over 0.06 meters, and that is going to be negative 16.7 diopters. Okay. Stop me if I lose you. Okay. Let's just keep on plowing through. And that means that when it gets through here, it's going to have a K final
The image is too.
that is equal to
The lines are.
this plus this is gonna give me negative
Oh, it's gonna be.
20.42 diopters. Okay, and that's gonna be right here. Well, negative 20.42. That's going to look like it is 4.9 centimeters back. It's a negative radius, so that means it's going to be back here. 4.9 centimeters. So that's where the image is now going to appear to be coming from. Okay. So by the time it gets here to this mirror, it's going to have a radius of curvature of 10 centimeters plus 4.9 centimeters. And so the K initial for 3 is going to be negative 1 over 0.149. Okay. And that's going to be negative 6.71. Okay, and then the power of the third one is going to be negative 1 over 0.14. That's going to be negative 714.14. And so now my K final 3 is going to be, I add these two together, what I give it and what the lens does to it is going to give me negative 13.85 diopters. Now, when we deal with mirrors, there's a special little extra in that it's not what goes through the mirror, but what bounces off the mirror. And so suddenly the wave is going this way. And so if I get a negative value for my K, the center of curvature is going to be behind me. Whichever direction the wave is going, negative's behind you. Okay. Now, I got to tell you, the old-fashioned way of doing this, the way most textbooks cover it, with a 1 over DO plus 1 over DI, but the rules are just crazy. You know, is it to the left? Is it to the right? Is it where the light exists? Is it where the light doesn't exist? But with curvature, it's just, hey, if it's spreading out, it's negative curvature, and that means the radius or where the light appears to be coming from is back behind me if it's going this way. Okay, so if I take that 13.85 and do 1 over it, I get 7.2 centimeters. And so it's now looking like there's a virtual image back here that is 7.2 centimeters behind. And the wave is now going this way. And now we gotta go through the two lenses again. Thank you very much. Okay. And so let's go down here and say when I get here to lens 2 again, but I'm going to put a prime because we're coming back around. That's going to be negative 1 over. I've got 7.2 centimeters here and 10 centimeters to get back to this lens. So that's 0.172 meters. And that's going to be 5.8. And it's gonna be negative. Diopters. Now, I've already got the power of 2. The power of 2 is still gonna be negative 16.7 diopters. And so when I add those up, I get a negative 22.51 diopters. Let's just forget about the 1 there, okay? Negative 22.5. That's going to appear to be 4.4 centimeters behind the lens because the wave is going, the wave is now going this way with negative curvature. So when I figure out the radius of the circle that it's part of, it's behind. So it's going to be right here. This distance is going to be 4.44 centimeters. Okay. Now that's going to propagate to this lens, and it's got to go 20 centimeters plus the 4.44. So I'm going to plug in 24.4 centimeters or 0.244, and that is going to now give me a K initial 1 prime of negative 4.098. Okay, so this is going to be negative 4.1. Okay, and then we said that the power of this was a plus. Oh, look at this, look at this. The power is a plus 5.55. Oh, come home to mama. We have a K final 1 prime of positive 1.45. Good, 1 out. After all that negativity, we have a converging wavefront on this side, and it's going to converge down to a real image, and that real image is going to be a distance of, holy smoke, 69 centimeters away. Way the heck and gone. Okay, I have no room on the paper to put that. I gotta move the paper out here, and there's gonna be a real image out there. But it's real because that last curvature is positive. I know that the waves coming out of here are eventually gonna, and that means that the rays are focusing down. Good, sir.
So if we were to do the height, we don't have to actually do it, but because it's so far away, the height of that image is gonna be a lot smaller than the original.
I'm sorry.
Is the height of that one gonna be a lot smaller because it's so far away?
Yeah. No, a lot bigger. Remember, further away is bigger. You almost had me there.
Oh, it'll be taller?
Yeah. Yeah. Because the image that formed it was
Where is it?
just right here. And so that distance versus that distance is going to give me the similar triangles.
And then how do you tell if it's inverted or not? No.
Sort of.
All right.
I mean, you can. The first image was a virtual image, so it's upright. And then the second one was a virtual image of that virtual image, so it would also be upright. The third one was a virtual image of that virtual image, so that would be upright. All of them were virtual until we got to that last one, so it's gonna be down. But to check myself, because there's so many minus signs in there, I would do a ray diagram, but we're not gonna do ray diagrams, so I'm never gonna ask you, is it up or is it down on the exam? And promise, cross my heart, Boy Scouts honor, I was an Eagle Scout, okay?
I wanted to ask questions from the practice sets.
Absolutely not. Sure.
Can you question
Two. Question two. I will try. I will do my best. Were you the one that sent me the email that said that this was ruining your life? No, okay.
Wrong 6 times.
6 is many. Okay. That's. If we were talking cows, that would be a wonderful wife. Okay, you probably are too young to know that movie, right? Mahana you. Every time we went to the temple as young people, we had to watch that movie. Johnny Lingo. Okay, so this is not going to be on the exam, but my daughter was thinking of marrying this guy. She didn't. Thank heaven. But he came to our house and he wanted to see me, and he put down a mat and he had me sit down on the floor, and then he started bartering for my daughter with frozen hamburger patties. I was so glad she dumped him. Oh man, he was a mess. He has a wonderful husband now. You might say he's a 7-cow husband. Okay. Let's look at this. You have completely polarized light of intensity. What number did you start with?
242.
242 watts per meter squared. What will the intensity be after passing through a polarizing filter with its axis at an 89-degree angle to the light's polarization direction? Well, I would say that the intensity would be I0 times the cosine squared of theta. That's going to be 242 watts per meter squared times the cosine squared of 89 degrees. Do we expect a big number or a small number here? Yeah, 90 degrees is going to give me 0. And so 89 is really, really close. So I'm going to type in, make sure that your calculator is on degrees. I've got it on rads here, so radians. So I'm going to change mine to degrees. No, that changes to grad. Now it's degrees. So I'm going to hit 89 cosine squared, and then that gives me 0.0003, and then I multiply by 242, and that gives me 0.0737 watts per meter squared. That what you got?
Yeah, that's what I did every time.
And it didn't work?
Something's
Oh, that's on me. Okay.
What's the answer?
So this isn't as hard as you thought it was.
Yeah, it doesn't tell you.
Yeah.
I've tried it. I've got something similar. What it gives you in the problem is in watts per meter squared. The answer's in mils.
Oh, it's oh, I see. So it's a conversion. It's this is the reading. reading comprehension. So this is milliwatts. And so I need to multiply this by 1,000. And so I would get 73.7 milliwatts per meter squared. Thank you. Is that what it was?
Yeah.
Oh.
But I can't submit it anymore.
So it's not on me.
No.
Oh. That's so sweet. That's so sweet. Thank you for that. I feel really good.
Are you over that atomic problem from the practice that you did in class?
Yeah.
Can we, wait,
The one with the zooms.
This one here.
No, the one in class that you do with the Z.
Oh, with the Z? Okay. Sure.
can we quickly just do part B for that?
Oh, you want to, can we do part B before we go on here? If we place another polarizer in between the light and the first polarizer, which you don't move, and what angle did you put in there?
I think mine was 60 degrees.
What's that?
60?
60 degrees, okay? Well, now, we're gonna first do cosine squared of 60 degrees. And that's going to give us, do we want to use 242 again, or what number would you use, like, to use for the?
Use 242.
242.
It would just be the same thing as the first time, basically.
Okay, so if I do 242 watts per meter squared times cosine squared of 60 degrees. Now I hit 60 cosine squared, that's 0.25 times 242 equals 60.5 watts per meter squared. And then this will be after the first one. And then after the second one, we take that 60.5 watts per meter squared. But now, what angle do I want to put in there? 89 minus 60. Yes, thank you very much, Miriam. So that's going to be 29 degrees. And that makes all the difference. Because before we had almost 90 degrees. By going through that middle polarizer, we've now put the light in a direction that's not so drastically different from the next polarizer. And so we're going to get a much bigger number than we did in part A. So if I take 29 degrees, take the cosine squared and multiply that by 60.5, I get 46.28 watts per meter squared, not milliwatts, but watts per meter squared. And that was the point of this question, was that we, by putting that polarizer in between, even though we've still got that 89 degree polarizer, it's 89 degrees relative to ancient history, not relative to the last polarizer. That was right. Good. Okay. So we want to, yes.
I thought you only used the cosine square on the very last term.
No, you use it on every polarization except the first one. The first one just gives you half if you start with unpolarized light. But after that, every single one, so you've got to use the cosine square. Okay. I'm glad we had this talk before the exam. Okay. So instead of that Z, if I may, suppose we had 3 flashlights that are shining light in a, I can't draw, we've established that. And one is sending out red light, one is sending out green light, and one is sending out blue light. And if I have a white screen, okay, but that white screen is in a dark room. And so when I look at the white screen, I just see dark until I turn on my 3 flashlights, and then it's going to look white. Because I'm giving it red, green, and blue light, and red, green, and blue give me white. And so it's white light on a white poster board, it's gonna appear white. But if I hang a big old clay ball in between the screen and the flashlights, the red light is going to get blocked over here. And so I'm going to get a region of no red. The green light is going to get blocked somewhere here. So I would have no green. And the blue light is going to get blocked over here. So I would have no blue. Now, the place where I've got no blue, I still get green and I still get red. So I get green and red. So this is going to be, this is going to be a yellow shadow of the ball. So far, so good. This one is going to have red and blue, and so it's going to be again, I can't go up, I gotta go down, magenta shadow. And this one is going to get green and blue, and so it's going to be a cyan shadow. Now, the same thing would happen if I just had yellow paint on the wall. When I shine this, if I shine white light on that yellow paint, it looks yellow because it absorbs the blue. It's a blue sucker, okay? And that's what this clay ball is doing. It's subtracting out the blue. It's essentially blocking the blue instead of absorbing the blue. But either way, I'm losing my blue, and what's left is yellow. Yellow and blue are complementary colors. Likewise, green and magenta are complementary colors. Magenta paint is a green sucker. It holds on to the green, whereas the clay just blocks the green. And finally, the cyan is a red sucker. It holds on to the red and lets the green and the blue reflect off. Is that good enough? Okay. And that's the level at which you'll need to understand color for the exam.
Can we do one of the clocks on the train?
The clocks on the train,
Yeah,
the shootout,
the
you're
shootout.
gonna make me go through the shootout?
Yeah, I wanna go through Greg and Ron.
When? Okay, I told some of you, Ron's widow is showing up at our house as we speak right now with her fiance. And I have mixed feelings about that. So this, I really, this is personal. We're gonna go through this. So let's, let's take two different, frames of reference. Let's take the sidewalk. And, at t equals 0, Greg shoots. According to Sue on the sidewalk. Okay? And according to Sue on the sidewalk, at t equals 40 nanoseconds, Ron shoots. Okay? Now, what really matters is what happened on the train, because that's where the shootout happened. And so let's look at the train. Okay. At t equals 0, if Greg's watch clock reads t equals 0, okay, I've just taken that arbitrarily. If that's 0, then Ron's clock must be trailing that. Okay. According to Sue, when she looks, that is when she sees Ron's clock, it's going to have a different value than 0 on it. Yes,
Wait, Greg, are you in front or back? Are you in the front of the train or the back of the train?
I was on the back of the train.
Okay.
Yeah, the paragraph after that example in the book is switched, but in the example it's correct. I'm on the back of the train. And so what she found was that the change in time between those two clocks, which was L prime V over C squared. Remember, the sheriff measured L prime to be 30 meters, and the V was equal to 3/5 the speed of light. And so this gave us 60 nanometers. No, nanoseconds. Yeah, time is measured in seconds. So that means Ron's clock would read, if she looked through the glass side, she would see that it read negative 60 nanoseconds. Okay. And that's when Greg fired. Now, if we look 40 nanoseconds later in the sidewalk frame, well, the moving clocks are running slow. And so if the time difference between these two events in the sidewalk frame is 40 nanoseconds, the time difference here is going to be 40 nanoseconds times that relativity factor. But the relativity factor for 3/5 the speed of light is 0.8. And so that's going to be 32 nanoseconds. And so that means when she looks again at her clock being 40 nanoseconds, Greg's clock is going to have advanced 32 nanoseconds. So his clock is going to read 32 nanoseconds. But Ron's clock is going to read, it was reading when she looked here, negative 60. I have to add 32 to that. So now it's going to be negative 28 nanoseconds. And here's where Ron shoots. Okay. Now the two clocks on the train were synchronized. You know, they agreed what high noon was, that's when they agreed to show up, okay? And so that means, if we believe what's on those clocks, Ron fired before Rick. He's the one that needs to be punished. Greg was just defending himself. Okay? Complicated problem that would never show up on the exam. You know.
Brewster angle.
What's that? The Brewster angle is not hard to find.
I think you're ready to know that.
The Brewster angle,
And then that.
we can find from this equation.
The velocity of the thing, like the velocity of the
And one, okay? Did I put that on the equation sheet?
Yeah. Yeah.
Okay, so, if I have, say, N1 equal to, air, and N2 is equal to, what do you want to be? 1.33 water. So this would be, tangent of 1.33 over 1, and so, no. Skip that. Tangent of the Brewster angle is equal to N2 over N1. And so that means the Brewster angle is going to be the inverse tangent. I got ahead of myself of 1.33 over 1. And so here you want to make sure that your calculator is set on degrees. And indeed, there is absolutely no reason to have your calculator set for radians on this exam. Don't even think about switching it over to radians, always on degrees. The only time we ever needed it on radians is when we were using that approximation. Theta is approximately equal to tangent theta for small theta. But that's only if you're measuring theta in radians, okay? But we're never gonna use that approximation on the exam. So leave it in degrees. And so I just plug in 1.33, take the inverse tangent, and I get 53 degrees, which is the Brewster angle for water. Okay, now we could have any surface. It could be glass, it could be plastic, it could be diamond. I can't afford diamond. The others, yeah. But you just put that index there.
What is the Brewster angle?
What's that?
What is the Brewster angle?
The Brewster angle is sometimes called the polarizing angle. And so if I have, and I've got to be going from fast to slow. And what we find is that when a ray comes in at the Brewster angle, of course, it comes off at the Brewster angle because the angle of reflection is always equal to the angle of incidence. But the Brewster angle is such that when this refracted ray comes down, it comes down 90 degrees to the reflected, and that's how I got my formula. And when I come in with light that's polarized randomly, some of it in the plane of the board and some of it out of the board, the part that I can draw in the board, on the board rather, we call that the P polarization for plunge. It plunges down, and the S polarization, which is parallel to the surface, but perpendicular to the plane of incidence, is what you get left. S stands for, some people say skip, it's the one that skips off the surface. But actually it stands for senkrecht, the German word for perpendicular. Perpendicular to the plane of incidence. That answer your question? Yeah. So that's why you need polarizing glasses when you're out on the lake at certain times of the day, when the sun's just at the right angle, the Brewster angle, you're gonna get a lot of light that's polarized, and you can block that out with your sunglasses. Okay,
You do question 13, how to practice that?
I can. Okay. The average lifetime of a pi meson in a total frame of reference, you know, where it's at rest, is 26 nanoseconds. It was a mu meson in our experiment at MIT. So this is 26 nanoseconds. If a particular meson is moving with a speed of, what speed would you like there?
0.9768.
That's fast. Okay. So the first thing I do whenever I've got a speed that's given in terms of the speed of light is I calculate that relativity factor, 1 minus 0.9768 squared. And you know, practice that before you get to the exam so you don't make a mistake in the exam. You put type in 0.9768, you square it with the x squared button, and then this little button down here that says change it to negative, do that, and then you add 1, hit the equal sign, and then hit the square root. And I get a relativity factor of 0.214. Now, what do I do with that? Well, do I want to multiply or divide by that to figure out how long this thing is going to appear to live in the lab frame? That's what we're asking here is, as measured by an observer on Earth, that means, you know, someone that's not moving at 97% the speed of light. Okay, do I expect a bigger number or a smaller number? Than 26, a bigger number. So do I want to multiply or divide by that 0.2? Divide. I want to divide. And so I want to take my 26 nanoseconds and divide by 0.214. And again, I can use the 1/x button here. Times 26 is equal to 121 nanoseconds.
Meaning you would see it.
Seems like a long time. Okay, compared to 26. Now, what is the average distance it travels before decaying as measured by an observer on Earth? Well, because of that first postulate of relativity that we all got to measure the same thing for the speed of the pi meson. We all got to agree that it's going at 0.9768, the speed of light. What we don't agree on is how long it lived. Okay, but if I agree that it lived, if I agree that it's going this speed and it's going for this many seconds, 121 nanoseconds, I would find the x, delta x rather, is just going to be that speed times the time that it is alive on average. Okay, the mean lifetime. And so that's going to be 0.9768 times the speed of light, 3 times 10 to the 8th meters per second. And then I've got to multiply that by 121.4 times 10 to the negative 9 seconds, because I want to cancel seconds here. I have to convert the nanoseconds to seconds. And so if I take that and multiply it by 1 e to the negative 9, I'll show you what I'm doing here. Okay, that's the number of seconds that it's traveling, and it's traveling at 0.9768, the speed of light. And I've got to multiply by the speed of light. And that gives me 35.6 meters. 35 spelled with a 5.6 meters. Okay. And what distance would it travel if time dilation did not occur? Well, now I've got to take the 26 nanoseconds. Just times 0.9768 times 3 times 10 to the 8th meters per second. I can also do that by just multiplying by the factor of 0.214, and I get 7.61 meters. So good. How are we doing for time here? We're out of time. I actually have to go be nice to this guy named Mike.
That works.
I'm just gonna call him Not Ron.
Oh.
Hey, Not Ron, how you doing? Good luck, folks. I'll be in my office on Friday, but not tomorrow. And next week I'll be there. You too.
Not wrong.
Get through all of these final exams here. Then we-